Hi everyone, welcome to Mostly Math. Today we will be discussing the precise meaning of these two statements, which are in regards to general relativity and more specifically the Schwarzschild black hole. If you read any popular physics books, if they talk about black holes at all, they are obviously going to mention the event horizon, and they will say that it's a special place because not only can you not get back once you cross it, but because of the claim that space and time interchange roles inside the event horizon of a black hole, which intuitively means that the final singularity at the center of the black hole becomes a point in space a point in time rather than a point in space. And if you actually study this in a textbook of general relativity, you'll find the more precise statements, which is the components of the Schwarzschild metric change sign at the Schwarzschild radius, which is often cited, but it's so elementary that they don't usually prove it, or rather give some argument as to why it's true. They just expect you to find it out for yourself, which you can do, but it took me longer than I would like to admit to find out how to do this. So today I'm going to show you exactly why this is true in two ways. First, let's talk about the Schwarzschild metric, or rather just write down the form that we're going to be using. We're going to use d squared is equal to minus 1 minus the Schwarzschild radius, which we're calling rs, over r, dt squared plus dr squared over the Schwarzschild factor plus r squared d omega squared, where d omega squared contains the angular portions. This part is not going to be very useful in this video for reasons that we'll see in a moment, but this is the Schwarzschild metric that we're going to use. We see the important Schwarzschild factor 1 minus rs over r, and if we want the components to change sign, we need this factor to change sign at the event horizon as well, rs. But you can't simply plug in rs, since 1 minus rs over rs, actually, 1 minus 1, which is 0, which becomes infinite here and 0 here. That doesn't help us see the sign change. So I'm going to show you what we're going to do in a moment. First, I need some more room, and I'm going to tell you that we are not going to be using the radial components, the angular components. We're going to consider only radial trajectories. So for our purposes, the Schwarzschild metric will be this. This is a radial. Basically, this means that you're coming into the black hole on some kind of a straight line trajectory, or more precisely, of a fixed radius from it. Either way, it's an important simplification which we're going to use. And this is the sense that they're referring to in these two statements here. The angular portion doesn't have an impact since the Schwarzschild factor is not a part of it. All right. So first we're going to consider the Schwarzschild factor here at two different points. We're going to be outside the horizon and consider the Schwarzschild factor a very small distance away, and then do the same thing approaching it from inside. So basically, we just want to evaluate the limit as r goes to rs of the Schwarzschild factor, which doesn't exist, but we'll show that it changes sign. All right. So outside the horizon, we're going to let r be equal to rs plus epsilon. So it's just a slight ways outside of the horizon. We're going to let epsilon be infinitesimal as well, since we essentially want to take a limit. So this means that epsilon squared is equal to 0, and that any small constant times epsilon is equal to epsilon. Just the standard rules of infinitesimals. Since you can't make epsilon any smaller by multiplying by some constant, like 7 epsilon is just as small as epsilon, so the 7 doesn't matter. All right, and now we're going to look at the Schwarzschild factor here. 1 minus rs over r. And we're going to actually let r go to a notation here. R is going to Schwarzschild radius plus epsilon. All right. This goes to 1 minus rs over rs plus epsilon. Or multiply top and bottom of the second term by 1 over rs to become 1 over 1 plus epsilon, since we had epsilon over rs being equal to epsilon, since we can't make epsilon any smaller. All right, and now we're going to use the geometric series formula. 1 over 1 plus x is equal to 1 minus x plus x squared minus x cubed plus etc. To conclude that 1 over 1 plus epsilon is actually equal to 1 minus epsilon. This is a very important formula which you can derive easily from this. It happens in physics all the time. It's useful to know. It's 1 minus epsilon, which is plus epsilon, which is great. We can also evaluate this heuristically for a heuristic argument. We would say that for this example, we have r greater than rs, which will tell me that rs over r, which is what we need in the Schwarzschild factor here. Okay, if r is greater than rs, then r goes to infinity, so this goes to 0, so it has to be less than 1, which tells us that the Schwarzschild factor 1 minus rs over r has to be greater than 0, which gets us the sign of the plus epsilon. The more complicated argument is useful since sometimes you need an explicit form of the metric, which I'll write down for you now. This basically tells us that ds squared for r greater than rs is equal to minus epsilon dt squared plus dr squared over epsilon, which looks very simple indeed. Now I need some more room here, so I have to erase the Schwarzschild metric. But it's basically this, with the Schwarzschild factor being replaced by epsilon. We have no sign change outside of it, so nothing unusual happens. Inside the horizon, however, we're going to let r go to r minus epsilon. So we're starting slightly inside the horizon and approaching rs as epsilon goes to 0. So this tells us that 1 minus rs over r now goes to 1 minus rs over rs minus epsilon, which, as before, multiplying by 1 over rs is just 1 over 1 minus epsilon, which by a similar geometric series argument, 1 over 1 minus x we all know to be 1 plus x squared plus etc. And for epsilon infinitesimal, only the first order terms matter. So 1 over 1 minus epsilon is equal to 1 plus epsilon, which is minus epsilon. We get our sign change. Great. So then ds squared for r less than rs is going to be epsilon dt squared minus dr squared over epsilon. So we started with the positive signature of the metric on the outside, and when we approach it from the inside, it is the negative signature of the metric. And this is what the textbooks mean by the metric changing sign. This is what the popular science authors mean by space and time interchanging roles. They are referring precisely to the sign change. I just want to note here, the approximation of epsilon being infinitesimal is basically setting rs equal to 1. And if you wanted a more precise version of this, you could always put it back. You could always write ds squared for r greater than rs is equal to minus epsilon over rs dt squared plus dr squared over epsilon over rs, which I don't think is as clean, and we don't really need it for the purposes of the discussion here. But some textbooks have it in this form. I just wanted to let you aware of that. And you could always put the rs back by dimensional analysis. And yep, one more thing to mention for you. So I just wanted to mention that the sign change only applies for Schwarzschild solution and perhaps some other ones, but you don't actually want the sign change in a metric that is fully analytic. In particular, there are other coordinate systems that don't have this, like the Krustal coordinates. These actually do not change sign at the horizon, so they show that the singularity isn't really a singularity at all. It's just a coordinate artifact, which we actually covered in a previous video. This is just another way in which the better do not change sign. At r equals rs. So basically, the sign change is just a feature of the Schwarzschild metric, actually an unattractive feature. So the popular science writers are sort of misleading the public in the sense that space and time don't really interchange roles. It's just that the Schwarzschild space and time coordinates change roles, and those are not the only coordinates that you can use. If you like this and want to see more, please subscribe to my channel. See you next time.